we've gotten to the point now where we can start actually talking about Spark and big data. And I want to be clear what I mean by big data. For me, the definition is something is big data if the data set and or the processing of the data set requires more memory than what you have on a single machine. So in other words, we have to distribute it across many machines. That's the working definition that I have for big data. Now, of course, that's not precise. You can easily, assuming you have enough money, buy machines that have multiple terabytes of RAM. Okay? But most of us don't own those. Most of us own machines that are much smaller, and in fact, it's generally much more cost-effective to have machines that have a smaller amount of memory. There's generally a sweet point for memory. Right now, it's probably between 32 and 64 gigabytes. Instead of buying one machine with a large amount of memory, you buy multiple machines that are in that sweet point and link them all together in a cluster. And that's really what big data is all about. Now, the birth of big data really came when some researchers at Google published this paper that appeared in 2004 on this method called Mapreduce. Now, Mapreduce was an approach to dealing with very large data sets. And to understand why this is significant, we normally think of our computers as being fairly reliable. So if you go out and buy a computer, odds are you'll get close to 3 years of usage before anything breaks in it. Okay, you might get more, you might get less, but saying that a time to failure is about 3 years is reasonably accurate. I want to estimate 3 years as being about 1,000 days. Okay, so that's fine if you own one computer. And that one computer is going to be highly reliable for on the order of 1,000 days. But when we start talking about large clusters of machines, when we're working in that environment, and that's the environment that Mapreduce was aimed at, where you make clusters that have thousands of machines, and to keep the math simple, we'll just go with 1,000 machines. I want to make a cluster of 1,000 machines. Now the time to failure, the odds that one of my machines will go down, is now 1 day. Okay, basically, I am going to expect one of these machines to fail every single day. And that has a big impact upon how I process things. I can't just start something off and assume that my computer, in this case a large cluster of computers, is going to continue working the entire time. There's a good chance that some part of it is going to die, and I have to be resilient against that. I have to be able to recover from that situation. That's the way that the Mapreduce algorithm worked. It allowed you to do some processing and then save the results off, and then do some more processing from that and save those results off, and do this repeatedly. And they showed that they could do pretty much the vast majority of computations that you'd want to do with more or less efficiency. Some things worked very well in it, some things are less efficient that way. And the primary implementation of this Mapreduce algorithm was Hadoop. And so Hadoop is still very broadly used. In fact, it's so broadly used that now Hadoop isn't really just an implementation of Mapreduce, which is kind of what it started as. There's an entire ecosystem of Hadoop that includes things like how you run a cluster of machines, Yarn, or how you do data storage, the HDFS. So there's a lot of aspects of Hadoop that go beyond just the Mapreduce. Now, there is a challenge with the way that Mapreduce and Hadoop work, though, and that is that part where after doing the reduce, it saves the results off to disk. And to understand why this is significant, it's important to look at latency numbers. So this is a nice little collection of latency numbers that is kept and maintained by Jonas Bohner. And here we have a list of different types of operations that can happen and roughly how long they take. So for example, if you have to fetch something from the L1 cache, which is the smallest cache that is closest to the processor, that only takes a half a nanosecond. This is a very fast operation. Of course, these are rough numbers. But if the value isn't in the L1 cache and we have to go out to L2, it goes up to 7 nanoseconds. If it's not in the caches and we have to go to main memory, we're looking at 1,000 nanoseconds. Now, when we're just dealing with a single computer, those are the long latencies. Generally, our entire computation will fit in main memory, and so everything that we're dealing with is on the order of 100 nanoseconds. Now, that's still a long pause. You're sitting there for several hundred clock cycles just waiting to get stuff from memory, and this is why languages that are best in performance often allow you to have the most control over where things go in memory. But once we go to a distributed environment, we have to do things like send stuff over a network. And then we're talking many thousands of nanoseconds. Or read and write large chunks of memory from disks or to disks, which is what Hadoop does. And then we're talking about potentially hundreds of thousands of nanoseconds. So, these things add up. And the goal of the problem with Hadoop is that it kind of slows down the computation because it spends a lot of time doing these disk operations. And of course, this is an SSD. If you were to actually have a rotating disk, we're talking about millions of nanoseconds in order to wait for the disk to spin all the way around when you want to read things. This is basically where Spark comes in. So the Apache Spark was originally born as a project at Berkeley, and then after it had gained a certain level of maturity, it was moved over to be an Apache project, and it's now the most active Apache big data project. And the key to Apache running, as you can see here, runs programs up to 100 times faster than Hadoop. The key there is because Spark does a lot more of its operations in memory. So while it's still distributed, it still has to do communication across the network, it doesn't save very often. And so the way that it does this is through these things called RDDs, which stands for the Resilient Distributed Data Set. We're going to come back and we're going to look at RDDs and what you can do with RDDs when we actually start talking about the technical details of playing with Spark. But it is the fact that it does most of the operations in memory and that it has a different way of making things resilient. So we still have the same problem. If we go to a cluster with 1,000 machines, there's a good chance that one machine is going to die every single day. And so we have to be able to deal with that. Spark deals with it in a fundamentally different way than Hadoop, which allows us to still do the majority of our operations in the memory of the machine and only go out to disk occasionally when we need to. And that gives us this remarkable speed benefit. And so that's why we want to talk about Spark. And that's why Spark is so popular as a big data framework. So we'll come back and we'll look at how you can get Spark, how we can include it in our project, and then we'll start writing some code that actually utilizes Spark, at least somewhat. We'll do it non-clustered to start with, but just so you can get a feel for how to work with Spark as an environment for doing data analytics.